Another round of applause for Wanseob, please.
Okay, thank you. So actually, this talk is about the open questions in the recent ZK world. And this might be a little bit theoretical, but I will try to explain it as much simple as possible. So the first question is about what else are the primitives that we can implement without arithmetic circuits. I'm going to explain what is using the arithmetic circuits. And also the second question is about maybe what kind of a primitive algebraic chip we can customize. So yeah, let's try to go. So the first question, the primitives without arithmetic circuits. This is something about actually some of a primitives can be achieved without going through arithmetic circuits. The easiest example is the ECDSA that I just mentioned, because ECDSA is also a zero knowledge proof, which is also succinct, also non-interactive, but actually it's proving some relationship that you have a private key and also you have a public key, which is derived from the private key. Actually, if there exist some other primitive some gadgets, and if we implement those ZK gadgets using only the primitive polynomial IOPs without arithmetic circuits, then actually we can make it much succinct and much faster. I will give you more detailed explanation about what this means. So I have a good example, which is a algebraic rate limiting nullifier, and would like to explain what is rate limiting nullifier. And to understand this, we should visit about the Shamir secret sharing and the polynomial commitment schema a little bit. First of all, rate limiting nullifier is a tool to protect ourselves from the DDoS attacks, spam attacks, when we have a network level privacy, which means imagine that we have a network level privacy, which means the server does not know who is requesting the information. In this case, the server is has there exists an attack point for those attack, because people just can request thousands, millions of times for some information. And to prevent this thing, we can have some spam protection layer, which is called rate limiting nullifier. In this case, let's say a requester has a private key, which is small s. And then requester will create a polynomial f of x, which degree is less than d. And then also the relationship here, the f of 0 equals your private key. And then when the requester requests something to the server, let's make the requester submit f of m, where m is the message, maybe hash of message every time. Then what will happen? If the requester shares more than d f of m, then actually the server can interpolate the polynomial, and server can just compute the polynomial. For example, you can, if you have 2 points, you can compute a line. And if you have 3 points, you can compute a parabola. So if you have a d point, you can compute a d minus 1 polynomial, because we can interpolate. So this is something that how we can prevent the requester spam too much, because if the requester shares too much, then it will leak the privacy, because we can compute the polynomial and we can just compute f of 0 and it will become the private key. This is what is Shamir secret sharing, and also what is rate limiting nullifier works. So rate limiting nullifier is currently using zero knowledge proof to make sure that the relationship is true, which means actually you don't need to take care of these equations, that the requester share the f of m, and we need to make sure that that f of m is computed correctly from a given polynomial. And also the given polynomials evaluation at 0 equals the private key of a given public key. These are the relationship that we would like to prove. And currently, rate limiting nullifier is using a ZK circuit to prove this. Yeah, I mean, the ZK circuit is a kind of a plus, a minus of arithmetic circuits to prove this relationship. But actually, we can implement this relationship without going through the arithmetic circuit, because we can define the relationship between those informations using only the polynomial identities, which is something like left-hand side equals the right-hand side, and we can evaluate that at a random point. And if the evaluation values are equal, then actually we can think like the polynomials of left-hand side equals the polynomial of the right-hand side. So actually we can call this as a algebraic rate limiting nullifier, that requester shares an oracle, actually, which is you can think this oracle f is a hash of your polynomial f. And also requester shares a public key. And also in this case, requester shares a nullifier n for each message m. And then we can query to that oracle f that f of 0 equals to the private key, and also which means g to the f of 0 equals the public key. And also we can query a proof to the oracle that is nullifier n equals f of m. This is all about the polynomial relationships. And we can prove this using a KGJ polynomial commitment scheme, that prover, this is something when we use a prover wants to prove that you have a polynomial and its evaluation value at x1 equals to y1. How to prove that? Is that verifier picks some random number r and make some powers of that random r and compute a elliptic curve point, which is hiding the exact random number. And this is a set of the elliptic curve points. And actually, after verifier shares the set of elliptic curve points, that actually the requester prover can compute the f of r using those set of a elliptic curve point. And the result will be also something elliptic curve point. And also after that, the prover shares a quotient polynomial q of x, which is a f of x minus y1 divided by x minus x1. Because actually, if you just put x1, evaluate the both side using x1, then actually left-hand side should equal to 0 and right-hand side should equal to 0. And we are evaluating this polynomial identity at a random value r. Actually, this is all about the zero knowledge proofs and what we are doing in ZKP. We are evaluating the polynomial identities at a random r, and if the both side equals, then actually we can assure that this polynomial identity holds true. Then actually we are, and the next part is adding a zero knowledge part So because we don't want to share these whole values, so we are sharing those values into a hidden form, which is called homomorphic hiding, and which is also in the form of the elliptical points, and we can check that using some special techniques, which is called pairings. So here the takeaway is that polynomial commitment scheme allows us to create some relationship without revealing some its detail, and also what implies to us is that we can actually build some special types of polynomial identities for some primitives. For example, this rate limiting nullifier, because we could achieve a same thing using only these polynomial identities without writing some ZK program. Because ZK program is have a lot of some extra computations to prove that. And this is much succinct and much faster. And its subsequent question is that, okay, we could do the algebraic rate limiting nullifier, then maybe we can also implement the algebraic semaphore. And I think I also need to explain what is semaphore here. That semaphore is a anonymous voting protocol. So first, you construct a group. Mostly it should be something like Merkle tree, group of identities using the public keys. And then from the public key that you have committed, we create some ephemeral identity. Actually, exactly saying from your private key. We should drive an ephemeral identity for each poll. So, and after creating an ephemeral identity, you sign something with your choice for that poll, then the signature can become a nullifier. Actually, it's something becomes a proof and also becomes a nullifier that prevents you to vote twice. And also, we can keep the privacy here that we are creating an ephemeral identity, and we also prove that that ephemeral identity is derived from the membership group without revealing what kind of public key or private key used to create that ephemeral identity. This is what the semaphore is doing. And the key ideas to make this semaphore, actually we are doing everything. We are proving this relationship that I explained inside of a arithmetic ZK circuit by writing a program. And our mission is that, okay, let's try to define some polynomial identities relationship equations rather than writing a program circuit. And key ideas to implement semaphore without circuit is using a polynomial identity, polynomial commitment as an identity, and making the evaluation of the polynomial at a poll ID becomes the nullifier for that poll, because you already committed your polynomial, for example, f sub Alice of x, and if Alice wants to make wants to vote to a poll, then should make a formal identity, which is something like f sub Alice of m, or maybe poll ID. So after that, we construct a membership group using the polynomial commitments, and then after that, actually to hide some information there, we can use Peterson commitments, which is something the Coq approach, or we can also use inner pairing products here to make sure that you are trying to use the same polynomial commitments. Also, you are evaluating that, but what we would like to do here is that we would like to hide which polynomial commitment you are using to make that a formal identity, is what we would like to do. So actually, yeah, there is a potentials that we can re-implement those kind of things using only polynomial equations identities without circuits. Yeah, so just recap of the first question. The primitives without arithmetic circuits, that actually we have a many primitive polynomial IOPs, which is something like polynomial IOP is something like you are proving some relationship between polynomials. And the polynomial IOPs that we have is every the polynomial is 0 for every point, or the sum of the polynomial evaluations of the polynomial equals to something, or we can do some batch opening or product check, permutation check, lookup argument. Also, we have some inner product argument like this. And the question is that, okay, then what kind of cryptographic primitive ZK gadgets we can replace using this polynomial IOP only approach? So this is the first question. And the second question is about the customized algebraic chip. It's related to the recent improvements in the lookup argument. First of all, as I mentioned at the panel discussion, there was a huge paradigm shift for the polynomial IOPs from the univariate setup to a multivariate setup. The most difficult thing for the univariate setup is that if you have a very, very big relationship, then you need to have a very, very high degree of polynomial. And also, as I just told you, that when you share something that through the KGG polynomial commitment scheme, you needed to compute some quotient polynomial. So dividing a high degree polynomial using some maybe low degree polynomial is also a pretty difficult work. And it takes time, and most of the proving time spent computing the coefficients using the fast Fourier transformation, and that is the most pain point for the univariate setup. But actually, we could convert that into a multivariate with a very low degrees. And then actually we don't need any kind of some computations for the coefficients. And actually we can express everything into a linear combinations, which is a much faster than computing the FFT. And there was also a big improvement in the recent lookup argument using the logarithmic derivatives. And I'm going to explain what the lookup is. And also there was another improvement, that adding GKR into the lookup. And actually what does adding GKR into the lookup means was something like, okay, maybe we can design some customized algebraic chip, just like we have GPU or ASIC for special purpose computations. I will show what this means a little bit in more detail. So I need to explain the recent improvements in lookup arguments. That lookup arguments is something that you are proving a set is subset of some pre-described table. And most effective way is, okay, we have some values and adding some random values there and multiply everything. And then actually it should equal to the multiplying everything in the table something. So this is a basic technique that we are trying to prove something is a subset of the pre-described stuffs. And what lookup did is transformed this kind of a product check into a summation. So actually, we can, if you just log a grand product, then actually it just becomes the summation of the log of each term, right? And then after that, actually they did the derivatives one more time and converted that into a fractional polynomial. And GKR, what GKR did is that actually in multivariate polynomial settings, it is pretty difficult to compute a rational polynomial. So it is not possible. So because of that, we define another multilinear polynomial and compute that using the interpolation. So actually we need to compute a auxiliary polynomials, many polynomials, and actually it was also a kind of a pain point for the computations. And actually this is what I explained, that lookup did just transform the grand product into the summation of the rational polynomials, and GKR actually did expressed the rational polynomial into the form of a polynomial identities. What does this mean here is that there's a P1 and Q1, and it actually it's a notation to express it's a P1 over Q1, and its parent node is the summation of its left child and the right child, and also it can be expressed as a P1 Q2 plus P2 Q1 comma Q1 Q2, and we can express this all the relationship into a simple polynomial identities using the GKR approach. And with this, actually, this is something what we have designed a specific electronic chip only for the fractional sum check stuff. And it can be used for the lookup arguments, and using that actually we can achieve a much faster proving time relatively doing the grand product check using the multivariate grand product check approach. So the summary of these questions is that CPUs are also the general purpose for general purpose computations, and zero knowledge proof circuits, the arithmetic circuits, are also for the general purpose computations. And we have seen the very two good examples for about how to replace the circuits using the algebraic formation formulas in the case of the rate limiting nullifier and also the semaphore, and also for the primitive IOPs, for example, lookup argument IOPs, actually we could design a specific gadget only for the lookup arguments, which is something like designing a special GPU. So my question is that, okay, what kind of other primitive ZK gadget or what kind of other primitive polynomial IOPs that we can design for the future is the open questions that I wanted to share today. Yep. Thank you so much. Do you have any questions?
Hi, Wanseob. Thanks for the great talk. It's very technical, and I believe I couldn't understand 90% of it, but I'm trying to understand some parts of it. I think regarding the semaphore example that you gave, at the end, you mentioned about Peterson commitment scheme or also the inner pairing product. So I was wondering, what's the difference between these the different commitment schemes? Like, can I also use KDG in that sense? And if yes, then which one is better, or how do I compare it? If no, then what's the reason? Yeah.
Okay, so Peterson commitment in the algebraic semaphore is something like you are already sharing a polynomial commitment, and actually that is a elliptic curve point. And what you would like to do is that hiding this polynomial commitment exists in a set of group. This is actually what the lookup argument does, and the calc used is adding a zero knowledge for about its index inside of this given table using a Peterson commitment. So, which is something like you have a polynomial commitment, and Peterson commitment is you are adding another point here, random point. And then actually, if this Peterson commitment is computed correctly, if you do something using the root of unity, then actually it should equal to the equal to when you have exponentiated n times. So using that factor, Coq could achieve the zero knowledge of the position. So actually, we are calling that a position hiding linkability. And this is one technique that we can do some membership proof without while hiding its exact position. So it can be used for semaphore approach definitely, because it's something anonymous membership proof stuff. And also inner pairing product is something an inner product argument for the pairings. And inner product argument itself actually has a zero knowledge characteristic inside of it, because we can adding some random and fold it and fold it and fold it again. So eventually we're gonna have a one instance which is folded using the random linear combination. So actually the verifier cannot know what exists inside of the vector of it. So this is the ideas that we can use for the algebraic semaphore. But I guess this is still in the work in progress. So there might be some mistakes. Yeah.
Thank you.
I'm Victor. Thank you for the talk. So my question is, this polynomial equation can replace arithmetic circuits in terms of zero knowledge calculation. Can we use polynomial equation to design a zero knowledge GK-EVM?
Actually that's something my question. What kind of maybe in the ZK EVM we have a multiple opcodes, and actually lookup arguments is replacing something there. And maybe what other opcode that we can replace using those kind of polynomial identities is my question. So that's what I really would like to explore more.
We have another 2 minutes for maybe the last question. If anyone have burning question to ask Wanseob.
Hello, what's up? Thank you very much for the talk. I would like to ask you two questions. The first one, could you please help me to understand more the example that you give in the previous talk about putting a game in a PlayStation 5 and to make it provable? Maybe you can perhaps expand on it. And secondly, please correct me if I'm wrong, because from what I understood from the previous talk and from this one, is that by usage of the polynomials, you're avoiding the usage of some like a ZK circuit. So that is what makes the process faster. Or perhaps you can also explain on that. Thank you very much.
Yeah, so let me start from your second question. That I mentioned that our final goal is something like we would like to build a provable computer itself. Which means like you have a CPU, and what we would like to do is say, okay, the state transition of your CPU and the memory is correct. Actually, this is the kind of a final goal. If we can do that, actually we can prove everything. But actually, this is a little bit difficult for right now. So we are trying to implement that using only a subset of some opcodes for some VM, for example, like not VM, for exactly, especially for RISC-V. This is our approach that we would like to do. And if we can do this, actually any kind of program you write is provable. So this is the approach that we would like to do. And we are pretty confident that proving time is getting improved a lot. So it might be pretty feasible in a few years. And my question, actually, what I shared here is that maybe when we go into the implementing those kind of some provable computer, there might exist some primitive opcode stuffs, and maybe we can try to design some polynomial identity structures for those things. Was my intention here. And the first question you ask about the what about writing a game? Then actually what I expect from writing a provable game is that the programmers should not take care of the ZK part, not at all. Is something my what I expect from the programmers in the future. So I think did it answer your question enough?
Actually, not, because when you make the game provable, what is the benefits that's given to the gamer, for example?
To the gamer. So let's say you have a competition or contest that everyone should just participate in the contest, and we are just finding who is the fastest racing driver in the world, in the sim racing world. Then maybe you can just try that in your home and you can just submit your proof.
So you don't need to actually play the game. You just need to show the proof that you can be the winner.
Right, because yeah, it's proving that you recorded that lap time.
All right, I think we don't have any more time. So a round of applause for Wanseob for the beautiful
Thank you so
talk.
much.